So this is kind of where I want to begin this discussion, and I want to start by helping you understand that we're going to be a little bit more flexible in our reference. So imagine I have a boat, and the boat is traveling this way, 10 meters per second. And we're looking top down on the boat. We can choose a number of ways of dealing with the velocity of the boat. The velocity of the boat is a vector. And in assigning vector information to the boat, we can provide reference. I don't think it's a huge stretch for me to say that you guys understand what I mean when I say provide reference. I could say compare the boat's velocity to these two reference directions, north and east. Right? We have some agreed upon ideas about the way north, south, east, and west work. In fact, I could go further and say that this angle is 60 degrees. With this angle being 60 degrees, do you realize the boat is traveling at one speed in the direction of north and another speed in the direction of east? Right? It's got two distinct speeds. It's got an eastward speed and a northward speed that combine to give it this velocity. Guys, follow what I'm saying? You all agree the boat is traveling to the east in one speed and to the north at another speed. Thus, it's traveling in the northeast. One way to write vectors is to write the magnitude of the vector first and the direction second. For example, I could describe the boat's velocity as being 10 meters per second, 60 degrees east of north. This fixes the direction for me by giving us an agreed upon Cartesian system, north, south, east, and west, and then describing the boat's velocity relative to that system. I mean, you might want to say that it's 30 degrees from the positive x direction, but you understand why north, south, east, and west might be better for us. Because this could also be written as 30 degrees north of east. This phrasing, east of north, north of east, will not be persistent all year. We're using it right now to train you on how to deal with vectors in vector addition. Eventually, we'll be dealing with things like the plane is traveling in a flat horizontal direction, and it's going to do a dive 20 degrees below the horizon. Well, you might establish the horizon like this, and the plane's dive 20 degrees below the horizon. You establish direction, and then make reference to that established direction. I'm declining 20 degrees. So this case, we've established direction, north, south, east, and west. If you don't know where the east of north and north of east comes from, imagine the play on words here. Start by facing north, turn in the direction of east, 60 degrees. The English language doesn't work like that. So we combine the words differently, saying I am 60 degrees east of north. But this is how you would arrange it, right? Start by facing the east. Turn in the direction of north, 30 degrees. So in English, we would say 30 degrees north of east. Everything good so far? Because here's the thing. Eventually, I want to add that there is a current in the water that is 5 meters per second due north. I would like to find a way to take that information and give us the actual travel of the boat relative to a fixed point in space. What is the boat's relative velocity? Meaning relative to a point that's not moving. In this case, we would have to add the vector velocity of the water to the vector velocity of the boat. It's clearly going to push the boat off course. Everybody understand? This is what I'm going to need to show you how to do. It's going to take a little time to get there. I think you guys need some practice first. So one of the things I want you to practice real briefly is consider the boat again. And I'll give relative directions, kind of. Can you give me a way of representing the velocity of the boat 2 different ways, please? I got 6 minutes. All right, Viv, can you give me one of them? So 30 meters per second, and then 20 degrees south of west. I'm good for that. There's another one. So, Michael, can you give me the other one? All right. Well, we know that the other angle is going to be what? And what direction would I face first? And then what direction would I turn? So I'd turn towards the west. What direction would I face first? Would you agree, Michael, that the 70 degrees is going to be a measurement relative to south? Okay. So faced south first, turn towards the west, 70 degrees. So west of south. Good? Now, this part, this is just us trying to delineate direction. What I really need from you is for you to tell me how fast is the boat traveling to the west and how fast is the boat traveling to the south. That's what I really want. I want you to take the boat's vector speed and find components. Now, hear me out before you guys start running off, because some of you know where this is going, but some of you don't. And I want you to understand, you can establish any reference for your system and then break it up into components. You are establishing the direction. So I established west as something that I wanted to use in this problem, but I could just as easily, turn this whole thing a different direction and made whatever reference direction I wanted as part of my problem. South and west are something that we can all agree on, but you choose the coordinate system that you impose on the problem. Sometimes it's better to choose a coordinate system that's easier to work with. This one's not terrible though, so we'll work with this one. Now, by working with this one, I'm saying that there is a vector that describes just how fast the boat is traveling to the west. And there is a different vector that describes just how fast the boat is traveling to the south. We call these two vectors component vectors because they take the actual vector and give us a part of it, the part in a specific direction. You guys all agree the boat's traveling to the south, right? And you all agree the boat's traveling to the west as well. So I want to know how fast the boat's traveling to the west. Now, some of you know how to do this and some of you don't. Those of you who don't, your first job is to establish a triangle that could be used. I'm establishing 2 triangles. Either of these triangles could be used to do this job, the yellow triangle or the red triangle. Doesn't matter to me which triangle you establish. Your math class forces you to use a specific triangle. I don't. Because trust me, it makes no sense. We're always going to use acute angles. We're always going to use the easiest way to do this. So I don't care. Do you want to use the red triangle or the yellow triangle? If we're going to use the red triangle, then we're going to use the 20 degrees that was given. So the red triangle, Once you've established which triangle, you are establishing the angle that you're going to use for your trig. You're also establishing where the right angle is going to be. With those two pieces, each side has a name. I plan on teaching you how to do trig if you don't know. If you do know, you should be way past me by now and be done. For those of you who don't know, I'm establishing my triangle. My triangle has a hypotenuse that's length is 30 meters per second. The hypotenuse is the longest side of the triangle. The right angle is always going to be against one of your cardinal directions. With that said, the 20 degrees was given here. Making this the opposite side and this the adjacent side. You should already know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Your job is just to build it now. Figure out what you've been given and what you can find. That's your job. All right, folks, we will practice this a little tomorrow. I want you to be experts by the end of class.